Good afternoon, everybody. My name is Roger Frechette. I'm a managing principal at Interface Engineering, and I want to thank you for logging in today and welcome you to our third installment of our 2026 High Performance Buildings Educational Series. Today's presentation is called Building Systems for a Changing Climate, and it'll be presented by Principal Steve Gross and Jesse Augusta and Associate Kylene Rockwell. But before we get started, I have a few housekeeping notes. One, to let you know we are using a GoToWebinar meeting platform, and all the audience microphones will be muted during the presentation. However, we do want to hear your questions, so please gather your questions together and enter them into the questions field. There are two different versions of the GoToWebinar. So depending upon which version you use, you will either find the questions field at the top bar or with the chat box that will pop out of the control panel. So the image here, you either have the left or the right, but either way, please submit your questions. We will leave 10 to 15 minutes at the end of the presentation to answer those questions. And if there's too many to answer during that time, we will distribute a Q&A summary to all attendees after the presentation. So today's presentation will be recorded and made available through our website and our YouTube channel. And Interface Engineering is an approved AIA CES provider. So for today's participation, you will earn one learning unit, HSW, Health, Safety, and Wellness designation. All attendees will receive a course completion certificate, or if we already have your AIA number, your attendance will be reported to AIA for you within the next 2 weeks. Interface Engineering is a 100% employee-owned mechanical and electrical engineering firm specializing in high-performance building systems. We have 12 offices nationwide and a team of over 200 professional engineers and designers. We focus on sustainable design and occupant well-being, partnering with clients to deliver practical, innovative solutions that create optimal environments for life. So again, today's presenters will be in no particular order. Steve Gross is a principal with our firm. Steve is the principal in charge of Interface's building performance team, specializing in energy modeling, thermal comfort, high performance system design, with deep expertise in LEED and net zero and passive house projects. Kylene Rockwell is an associate and senior building performance analyst with Interface. Kylene combines her experience as both a professional engineer and architect to deliver advanced building performance modeling and analysis that directly informs practical high-performing design solutions. And lastly, but not least, Jesse Augusta. Jesse is a principal mechanical engineer focused on right-sized, high-performance HVAC systems for healthcare environments, with particular expertise in controls, system optimization, and resilient design for resource-constrained facilities. Designing for tomorrow's climate means integrating future climate data into energy and thermal comfort modeling to create more resilient, cost-effective MEP systems. So with that, we're going to dive right in. I'll turn it over to presenters and enjoy the show. Thank you.
Thank you very much, Roger. Good afternoon, everyone. Glad to have you here with us. We're going to get started, and I'll just start by showing our agenda here today. Oh, by the way, I'm Steve Gross, so thank you all for coming. Our agenda, we're going to set the stage about the topic. What are we getting into today? You're going to hear from Kylene to talk about how we incorporate future climate data into our analysis process. And then Jesse's going to talk about some design strategies and how we select amongst them to fit the project. And then a case study I'll close out with on a project that we did at San Francisco State University where we incorporated this framework that we'll talk about today. Here's our full course description, which I won't read through, but I've already given you the gist of what we're going to talk about today. So these are just more of the details. But we hope you, as attendees, walk away with some new knowledge that you can use in your practice. So we're going to explain the methodology of incorporating future climate weather files into our process, any project's process. We'll talk about a range of climate adaptive MEP strategies. Talk specifically about thermal comfort modeling and how the framework we've established we use to communicate with occupants and owners and all the stakeholders of a project. And we'll talk about addressing existing buildings needs as well. So to get into it, we'll set the stage today. As we know, our Earth has experienced many different climatic changes over its history, and now as the climate scientists have warned for many years, we seem to be entering into a dramatic warming period after having gone through a cooling period. So I think many of us have had this sense that the last 10 or 15 years we're experiencing rising temperatures and longer heat waves. And so we pulled together some data to kind of support what we're seeing and feeling out there. So this chart is called the warming stripes, and it's just a simple way of looking at how recent temperatures or temperatures over our history have changed over time. And so it's comparing every year against an average temperature. So the average was established in 1971 through 2000, those historic temperatures. And a blue bar would indicate a year that was colder than that average, and a red bar would indicate a year that was warmer than the average. So you can see from this chart that we went through, the Earth went through a cooling period in the mid 1800s up to the mid 1900s. And then as it leveled out, sort of the middle of the 1900s, and it's been since generally warming. And you can see the more extreme years, the darker red colors in the last 5 or 10 years, just kind of indicating where we've been over the last while here. And I think this would jive with most people's experience of hotter temperatures and longer heat waves. And some more data. This is digging specifically into the United States, a study done by our federal government and characterizing 50 of the largest cities in the United States. And what it's showing is heat wave frequency and the heat wave season length. So the top chart in orange is showing you the change in the number of heat waves per year. And so generally with a vast majority of these cities that were studied, they're seeing significant increases in the number of heat waves per year. And then further to that, the length of those heat waves are also increasing as we go along in time. So kind of steadily increasing since the 1960s. And unfortunately, the past 5 summers, we are inundated with headlines just like this that I'm showing on the screen here. So every year, millions of people are experiencing extreme heat stress across the country and across the world. So this bottom right chart we pulled yesterday, and it changes day to day, but yesterday 75 million people in the United States were experiencing or exposed to extreme heat stress. That's nearly 22% of the population, and it's happening at once. So schools and hospitals are struggling to stay open, and it's very common to see students and occupants sent home to take refuge away from the heat because these buildings are just not functioning properly when the temperatures get to these historic levels. But when our building stock has been designed based on these historical trends, our buildings are really no longer places that we can count on for refuge. So we as designers and architects and engineers have a very important role to help our clients and owners to address this problem head on with creative design solutions and forward thinking, and really break away from the historical standards and apply a new standard, a new way of thinking. So just to kind of recap how we've gotten to this point, or where we've been, how we've been designing for the last several hundred years. The industry-wide, worldwide, uses the ASHRAE standard 169 to establish design conditions. So what temperature we assume the building needs to maintain comfort, inside versus what the outside temperature is. All the envelope requirements and codes across the world are based on on the data published in Standard 169. So it's a very important document that's been used for a very long time. However, there's some, even within their own standards, it's acknowledged that this methodology does not account for or predict what's happening or what will happen in the future. So you can see my first quote there. How to use the trend estimates is left to the individual practitioners, as there is at this stage no accepted method for designing for future climates. And we will show you some methodology that we've been using and other industry partners have been using, but it has not been adopted as a industry standard, such as Standard 169 has been for many years. And it's important to understand that these design criteria that we use are based on historical retrospective data. And so even the most current version of ASHRAE 2020 Standard 169 from the year 2020 is based on data from 1986 to 2015. So that data we're using is effectively being averaged and dampened out by historical trends. And you can see from our previous slide on the warming stripes that if you're including those years when the climate was relatively stable and mild, it's going to create some issues for grappling with this issue of what's coming. And I do want to say I'm not bad mouthing ASHRAE. It's been the backbone of our industry for 130 plus years. There's many deep thinkers at ASHRAE that are grappling with this issue. However, the design standards really are still referencing historic data. And it's very important for all of us to understand and acknowledge that and consider how to work around that. So ASHRAE has done their own research into this trend, basically just commenting on what the trend is. And so this research paper studied the last several editions of ASHRAE fundamentals, where these factors and temperatures are published, and they've determined that on average throughout the world, we can expect about a 0.7 degree increase in design temperatures per decade. And so as you're looking, see that number of 0.7 or 0.68, and also looking at this chart, it might give you some discomfort that, is this standard actually reflective of what we're experiencing around the world? So climate design temperatures are generally slightly higher, indicative of a general warming of the climate. So, we have this trend. It is indicating the climate's warming, but it is retrospective and not necessarily considering some of the scientific analysis of where we're going. And so our next section here, next speaker, Kylene, is going to talk about some of that data that's available to us to utilize in our design process, and talk you through that. So take it away, Kylene.
Great. Thank you, Steve, for really showing us what's happening in the real world and climate change. I'll be switching us a little bit into what we're doing in our practice and design methodology. And so I'm going to make, hopefully, the viewers little climate scientists after this section, just going over some of the basics of climate and future climate information. And so we're using climate files in our energy models, and that's been common practice. But the typical meteorological year, TMY, is the type of climate file that we use in our energy models. And what a TMY file does, it's January through December, but it's taking the most typical month from a 15-year period and using that month in the weather file. And so this process really does intentionally remove extreme weather events from those TMY files. And then the TMY3 format, that's from the period of 1991 through 2005. And 10 years ago, we were using TMY3 files very commonly. And I do still see people using TMY3 files right now, but they have at least updated to TMYX, which is looking up until, at this point, they have until 2025 period of data. It's still, 15 years prior to 2025 is being accounted for in that TMY format, but at least it's, shifting us a little closer to present day. And then as we're looking at future weather, they have future TMY, so FTMY, and that's going to take the global climate models and actually shift those TMY files into what predicted science says our future climate will be. And then there is another process that we like to use is looking at an actual meteorological year. So, 2024, we actually had a heat wave in this city. And so we can take that AMY file from 2024 and shift it to the future. So then we do have extreme weather events that are happening in the future that can also be played into our models to see what happens with our building performance. And on our next slide, we are covering some of the different terminologies for greenhouse gas concentration trajectories. So we have RCP and SSP. They're both very similar in that they're looking at how much energy is going to be trapped in the atmosphere and how many degrees the temperature is changing on the planet. SSP does add another dimension of looking at societal impacts. So it's going to look at economic, urbanization, technology, and governance impacts. And if you've done like a little bit of carbon emissions modeling, you'll also hopefully be familiar with these RCP and SSP scenarios. But for both of them, the lower numbers mean that we're doing very well in terms of reducing our carbon emissions and that we're starting to reduce the temperature in the atmosphere. So that's the green line on the graph on the right is the lower RCP 2.6 and SSP 1. But then on the flip side of things, as we start to look at that purple line, that's starting to increase temperatures. Those are our business as usual. If we still have high emissions and rely on fossil fuels, that's going to be that extreme RCP 8.5 and SSP 5 scenario. And then what actually informs these scenarios is, as I mentioned, a global climate model, so GCMs. And there are numerous GCMs that are available to us. But the best practice for us is to, I think in the graph on the right, you'll see there's about 24 GCMs, and they have, very varying degrees of some outliers in our radiation that's getting predicted and humidity. And so they're not all the same, but ideally you would take an ensemble. So you would, you could take all 24, or if you start to dig into what each GCM really means, maybe you can fine tune down to 10 GCMs that might make the most sense for the problem you're modeling right now. But that's really the data the climate data that you're using to shift these weather files and get that future weather scenario that you want to include in your project analysis. Okay, so here we are looking at I call them annual heat maps. It's plotting every hour of the year. So you're seeing columns of months and hours of the day. And the image on the top left is that TMY3. This climate is an ASHRAE climate zone 3. It's in California, and it is also California climate zone 3. But it is a temperate climate, and you'll see in that TMY3 file from 1991 to 2005 that during the summer it's generally pretty comfortable. Winters there is some cold hours, and then as we go to the right and look at the TMYX, that is looking at 20-year step in the future, but still prior to our current day. That TMYX file, it's starting to lose some of those cold day temperatures. The dark green is going away. And then that comfortable period is starting to elongate. And so this climate is getting a little more warm. But you'll see even more so, the lower images are the future TMY files for this climate, looking at the highest greenhouse gas concentration trajectory, so that SSP 5. And then really looking at 2050, and then the lower right is 2080's future weather. And so, as we've all been understanding and feeling in our real world, the climate is warming in this climate, and we are getting less cold hours here for this project. And that's part of what we need to address in our design and engineering. Okay. Before we hit play on this video, I'm going to try to explain what we're looking at. This is one of our design tools, which is a parallel coordinates plot, and we can use this at all phases of design. In this case, we're looking early phase early phase in trying to inform building envelope decisions. And so this particular project has run 140 energy models, and that's kind of what you're seeing on your screen is the inputs and results of those 140 models. And we're looking in this case at exterior wall construction is kind of that second column, looking at the thermal performance of windows and then roof construction. And then adding on the layer relevant to our conversation today is also trying to see what happens with different weather files as we're running these models. And Steve, you can go ahead and press play and we'll see as we start to navigate. It is a graphic and dynamic way of looking at things. This project is, again, that's the same climate we were just looking at in California, and it is a student center. The results are the 3 columns on the right. So right now we're changing the color to look at operational carbon. So it's kind of creating a rainbow effect, and you can see what might be high in carbon is going to be low in energy costs. You can kind of see a weird triangle happening there with the results. And that is this building is using a gas hot water plant to supply heating. And that as we're going into the future scenarios, we're going to be using less heating and more cooling, so more electricity, and kind of having more expensive energy costs. Kind of in the video, we're using the sliders to show what's happening in the future weather. Those are kind of those top 2 weather files, and then we start to like set. If we keep our wall and roof at code levels, and then now I want to look at where can we play around with our window performance, where might it be more sensitive to the project and have more impact on our performance criteria of energy or energy costs or carbon. So for this example, we're looking at a lower solar heat gain coefficient than code, or a lower U value than code, and really seeing where our money might be best spent based on our performance criteria, not just for the TMI of today, but then looking at those future weather scenarios as well. And so for this project, we do see that the emphasis, even in the future, should still be on a lower U value on the fenestration. And so not to say solar heat gain coefficient isn't important, but it's not as important. So if we're going to choose where we're putting our money for this project and climate, current and future, we are prioritizing that lower U value. And that's just a little snippet of kind of what we do in practice with building envelope measures and future climate. Right. We will move on to Jesse in our next section, and he will be discussing climate adaptive design strategies.
Thank you, Kylene. Set us up nicely. So I'm going to talk about the climate adaptation design strategies. There's an old line, if the only tool you have is a hammer, everything looks like a nail. And that's roughly where our industry sits on sizing. We have one tool that we trust, ASHRAE climatic design data. And this, as Steve mentioned, looks back over 30 years of data and gives us an average or worst case scenario for us to design around. It's a good tool, and it's been the right tool for a long time. The problem isn't really with the hammer. The problem is that it's the only tool in our tool chest that we reach for, and then we swing it the same way on every project. This tool looks backward by design. It's built entirely from weather that's already happened. So we take historical conditions, add a bit of a safety factor, and call it sized. Every building, same swing, no matter where its climate is heading over the next 50 years. This works right until the nail isn't a nail. And as we just saw, the baseline is moving with higher peaks, more hours at elevated temperatures. The hammer still lands, but it's solving for a condition the building won't actually live in. Future projections that would let us see that have no home in our standard workflow yet. So the default holds and we keep swinging. So the better question is not how hard do I swing the hammer? It's not about how big of a safety factor I want to have. It's whether the hammer is even the right approach for where the climate is heading, and maybe we need a different tool to get there. So the rest of the section, we'll see what else is in our toolbox and I'll offer up a simple way for us to kind of decide which tools to use on a project that will actually fit it nicely. So let's move on to the toolkit. Now that we've named the problem, it's time to talk about what we can do differently. For those of you who've spent a good amount of time with sustainable design strategies, you'll recognize most of what's coming. These are established efficiency and resilience strategies, not exotic ones that I came up with for this webinar. What's deliberate isn't the list itself, it's that we select and sequence them against projected loads instead of the historical design conditions. And so each one of these strategies earns its place because as the baseline changes and our temperature is increasing, the effectiveness of these strategies also increase. None of them require predicting the future precisely. They're about building in flexibility so the building can absorb whatever the climate delivers over a 50-year life. So let's dig into each of these. We're going to start with envelope and passive strategies. This includes insulation, shading, and improved thermal mass. And we're talking about going beyond whatever the code says is the minimum, leading more towards passive house and extreme insulation strategies. And so as our weather is changing and our climate is increasing our temperatures, better insulation will prevent that heat from coming into the building. And then a higher thermal mass will delay how long it takes for that heat to actually enter the building, which brings us nicely to our next topic, which is night flush and natural ventilation. So with a night flush strategy, at night you open up windows and you pull the cool outside air through the building and relieve the hot air at the top. Throughout this process, the warm thermal mass of the building is releasing its heat and cooling down inside. So that way, if you have a really high thermal mass building, it can take a long time for the sun to warm it up the next day to the point where it's not uncomfortable. You couple this with natural ventilation strategies, and we will maximize the amount of time that we can use outside air to cool the building as a whole. This strategy relies on shifting the peak condition that the building sees. So on our next slide, where we talk about hybrid conditioning includes radiant floors with hydronic piping tied to a dedicated outside air system, or DOAS. This amplifies the night flush and natural ventilation strategy by improving the effectiveness of heat transfer at our thermal mass. So we're basically moving all of our heat transfer technology down to the floor or a radiant ceiling, where the sensible load of the space can be dealt with directly. The key is that the dedicated outside air system on the roof be sized for an increasing outside air temperature, not just with dry bulb temperatures, but also with wet bulb and relative humidity. If our insulation is good and we have great thermal mass, then we can rely entirely on our DOAS system to remove all of that latent energy that's being added to the system due to the increase in temperature of our climate. So moving on now to our next strategy, which is energy recovery. So with a heat recovery or an energy recovery system, the effectiveness of that energy that we can save back into the building improves as our temperature differential between what's in the building and what's outside increases. And so this is a great technology to have in place for the long-term use of the building. We can recycle a bunch of the energy that we've already put into the building. Next up, we have adaptive controls and automation. So this is actually a really exciting technology because if we have an advanced BMS installed at a building management system, we can respond to that extreme heat event dynamically. And that would mean, for example, we could have automated night flush, where we start the night flush earlier or later, depending on what's actually happening with the outside climate. We can alter comfort bands, i.e. change thermostat set points in spaces that are less occupied than others by looking at occupancy levels within a building so that we're prioritizing where people actually are in the building to maintain comfort. And then we can also do demand-based staging of different chillers or other systems in the building based on the expected weather data that allows us to get ahead of that heat wave coming in instead of being reactive to it later on. Next one is microgrid ready electrical infrastructure. The idea here is that we design the electrical system now for distributed generation and storage to be added later on if the budget doesn't allow for it to go in right away. So this allows us to hold critical loads in place while the grid potentially goes soft during a heat dome and we don't have enough capacity available from our central utility. So these 6 get filtered by project conditions, and these next 2 I'm going to talk about operate a little differently. So let's go on to the next section here. The future mechanical and electrical capacity and decarbonization ready design are both baseline design strategies. That means that no matter what other things we have thrown at us on the project, these 2 we hold to the core to make sure that we're setting ourselves up for success later on. Starting with future mechanical electrical capacity, the picture here sums it up nicely. We have a large enclosure area for a heat pump or air-cooled chiller on the roof, and we don't fill that whole thing up. So later on, 15, 20 years from now, as our climate is changing and we need more capacity, there's room to do it. And there's also structural support built in to allow for that to happen without a major retrofit to the building. There is a slight cost to this, obviously, by putting better structure in or taking up more space for mechanical systems. You pay for that upfront, but it is great. The saving is tremendous compared to the cost of doing this kind of retrofit work on an existing building with tenants in place. The next idea here is decarbonization ready design. And that essentially means that if we have to have a boiler or other gas consuming device, then we design the rest of our systems such that they can easily be converted over to a heat pump later on. That means lower supply water temperatures in heating mode and maybe a little bit elevated temperatures in cooling mode, so we can fit very nicely in where heat pump capacity hits its peak efficiency. So these 2 strategies will move forward no matter what. Okay, so after we have our toolkit, it's time to layer in our project condition variables. We have climate zone, building type, codes, budget, staff capability, and sustainability targets. And now that we have all of this overlaid on top of itself, we are kind of in this bit of a mess of where do we start? How do we choose the right type of system from the toolkit to match our building? And it gets very confusing. But this is where, as an engineer, I like to simplify things. And the best way to simplify this is to create a filter. So this is a classic filter problem. If we sequence our variables correctly, we can kind of get through this web of confusion and see a clear path. So let's see what that looks like. Here is the full filter. We have 6 strategies we'll put into the top and 2 baseline strategies that are going to bypass our filter because they're just part of our standard design process. There are 2 stages. Number 1 is our hard gates. These are things that are driven by code or climate and our owner, and certain systems just can't make it past these hard gates. What does make it through makes it to stage 2, our soft shapers. At this stage, we are applying a metric of value to each of the different options that make it through to see which one best aligns with our particular building. And just one quick note here is the gates and soft shapers you're going to see are generic in nature and need to be evaluated on a per project basis moving forward. So anyway, let's look at our first stage, our hard gates. And in this case, we have climate zone, occupancy, and code. So starting with climate zone certainly needs to be taken into account to choose the right type of system here. It won't eliminate everything or impact everything, but the things it does impact a great deal. For example, night flush and natural ventilation work really well in a temperate climate with medium cool temperatures at night. If it gets down to about 15 degrees, that's too cold. If it gets up, it doesn't get below like 85 degrees and we have a high humidity event, then night flush is not going to be highly effective. So that can be something that can pull out a system or amplify another system to stay in. The next stage is occupancy. Consider, for example, a hospital. If we had a hospital that needs to meet ASHRAE 170 requirements for ventilation effectiveness, we can't be changing our thermal comfort bounds for patients in a hospital or in an operating room the same way that you could apply that same strategy to a dorm room, for example. The last item is code. And for this, we need to take into account all of the local codes where our project is happening. Perhaps there is a Title 24 requirement or refrigeration requirement that would force us to move from one system over to another. After we've gone through that initial filter, through our hard gates, we can move on to the soft shapers in our second stage. So at this stage, nothing falls off. What survived before gets weighted against the three things I'm showing up here. We have staff capability, budget, and sustainability targets. Starting with staff capability, it's really important to understand what the capabilities are of the facility staff that are going to run the building after you're done with your design and the building is built. For example, if you put in a night flush strategy, but the O&M team doesn't understand how to do it, or if it even exists in the first place, you can end up with the system not working how it was intended to work, and unhappy occupants and unhappy O&M staff. So understanding the staff capability is a really important first step. Moving on to the second item here is budget. Now, this is a soft shaper because there are strategies that we can employ to push out deferred sustainability strategies to later on in a project. But a budget definitely could limit some strategies over others as it goes forward. The last item here is sustainability targets. If we have a LEED Platinum or Living Building Challenge project, then we are going to want to amplify envelope, say, for example, compared to really focusing in on a microgrid-ready infrastructure, depending on how the budget all plays out. So now that we've gone through all of the gates, and we'll go to the next slide, we are left with our viable set of options. And this is essentially where the deliverable ends. We have a layered and ranked system with primary, supporting, and baselines underneath each of them. And at this point, I just want to step back really quick and just point out that the filter doesn't make the future climate strategies. It's just narrowing our established strategies to ones that fit the building with this occupancy and this particular budget. And then we can select them and sequence them against where the climate is heading rather than where it's been. That's the core idea here. We find the right strategies through the rigorous filter, and then we can create a building designed from day one for the changing climate. Now, all of that without overbuilding or overspending on mechanical systems today. And that's our goal. So anyway, with that, Steve will show us how exactly this is done on a real project.
All right, thank you, Jesse and Kylene. So we're going to talk about talk about a real project where you implemented the frameworks and the data processes, decision-making process that Jesse and Kylene had talked about previously. So just to introduce the project, we're talking about a student housing, a dormitory building at San Francisco State University. It's about 750 beds, so not a small project by any means. And it's important to understand or know that San Francisco State and many other Bay Area colleges and universities have had a long-standing design criteria where no mechanical cooling would be provided for dormitories, and even for other buildings, sometimes even classrooms. So we've worked on quite a few projects with this type of approach. But what happened during this project was sort of serendipitous, as much as a heat wave can be. We were pretty fortunate that this heat wave occurred during design and during the part of design where it really mattered and where we could still make some adjustments. And this heat wave really raised awareness with all the stakeholders, and put this idea in their head that perhaps there was too much risk in following their design standards, and not providing any cooling. So we're going to talk through this. Just a starting point, this is where we started the project. Pretty typical, mild climate type of system where we're providing heating only, along with mechanical ventilation that's delivered at a neutral temp. So pretty close to, whatever the indoor air temperature. So in heating mode, heating season, we're delivering air at 70 or 72. And then in cooling season, we're delivering air at 75, 76 degrees. So that's typical, just to kind of limit the energy consumption associated with ventilation, limit the size of the equipment associated with the dedicated outside air system. We were planning for heating only radiators, so hydronic radiators served by an air source heat pump, as this building is an all electric. Was part of the design criteria, was to be an all electric building. And then we were providing operable windows so students could have some control over their thermal environment and get some passive cooling when outside conditions would allow for it. So it's a very typical design approach for a project like this. It's pretty cost effective, pretty simple to maintain and operate. So one of the first things that we did on the building sciences side of things was conduct a thermal comfort study, along with projecting our lead points and energy consumption. We wanted to try to reinforce what the implications would be from a temperature and experience, thermal comfort experience standpoint in this project. So this was from our schematic design energy analysis, and on this page we were comparing a few different things. So we were comparing 3 or 4 different orientations of the building. We were comparing with and without natural ventilation. We were comparing 2 different solar heat gain coefficients, as well as some shading devices on the exterior of the building to shade the windows during the summer months. So this example is from a south-facing dormitory. So we have overhang projections above the window, and then vertical fins on the western side to prevent the late afternoon sun, just knowing that would be most likely times when we'd experience overheating. And what the table here is showing you is the number of hours per year that the temperatures are expected or predicted by the model to be above 78 degrees, with 78 degrees being chosen as just the maximum desired temperature, where they could justify temperatures up to 78, and then temperatures beyond that would be difficult to justify from a design standpoint. So the first 2 rows you're seeing are just there for frame of reference. We're modeling the building without any natural ventilation, so it's just getting mechanical ventilation and heating only. So we see quite a few hours of above 78, so almost 800 hours with the higher solar heat gain coefficient. And you can see it actually is pretty impactful by letting less solar energy, it's obvious, into this space with a lower solar heat gain coefficient. That chops off a big chunk. But then again, just frame of reference, we were intending to provide operable windows. So the next 2 lines down are showing an unshaded windows, and then the 2 solar heat gain coefficients we were evaluating. So we're in the range of 200 hours over 78 degrees with those options. And then when we shade the windows, we're seeing that drop down another step, so 145 hours. And that's still, pretty significant, especially considering that, I'll show later, when those hours, time of year that those hours are occurring is typically, when the dorms are occupied. So another, sort of view of this data that we provide to the team is to look at when and how long that overheating is occurring. So from our historical weather data, weather file, it was predicting that the peak temperature outside would be 93, 94 degrees. And as a result, the inside air temperature would likely rise up to about 85 or 86 degrees. And we can see when that's occurring, starting around noon and lasting to about 6 or 7 p.m. We've got about 6 hours of time when the temperature is above that ideal time, set point. And this is also, the time when students would be coming back from class, looking to study, relax, rejuvenate, and those types of things. So sort of the least ideal time to experience high temperatures. So this was our first step of understanding what was going on with the project, and so we wanted to come back and think about our system selection. So as we thought about how to deal with this overheating issue in the dorms, we wanted to try to consider options that would deal with this, that would be in similar complexity, similar costs as well, that were adjacent to the types of systems that we had already designed and started with. So what we ended up with are came to mind here was two pretty simple interventions we can make. So we wanted to know what would be the impact is if we chilled our ventilation air. So instead of providing neutral temperature air during the summer, we drop that air temperature down to say 55 degrees and deliver that to the space. So we are talking about a relatively small amount of air just for ventilation, but nonetheless, you'll see the impact that that had. And then secondly, we looked at providing cooling to those hydronic radiators. So and I want to be clear here. So this strategy was not to add extra radiators to deal with a specific cooling load and maintain a specific temperature. We wanted to know, well, what if we just used the heating radiators that were sized just for heating and put cold water through them? How much impact would that provide? How much benefit would that provide? So that's the next stage of our analysis here. So again, we're still working with just current climate data, kind of the traditional design approach. And we've digested all of our modeling exercises and pulled data from our models and came up with these summary charts here. So option 1 was where we started, heating only. Option 2, cooling the DOS. And then option 3, providing partial radiant cooling through those heating radiators. So you can see that both of these strategies, option 2 and 3, were very impactful for dropping a significant, like 70–80% of those hours we were predicting would be over 78 are dropping off with these strategies. And so while we were in the midst of presenting this and helping the mechanical review board and ownership teams to make a decision on this, these were the headlines we were faced with. Literally in the midst of delivering and presenting these results, it was predicted to be nearly 100 degrees in downtown San Francisco. And if you're not familiar with that climate, I lived there for 10 years and can tell you 100 degrees in San Francisco is a very difficult situation and pretty scary for the folks that live there. Mainly because almost no places have, especially homes and residentials, do not have air conditioning, and even many commercial buildings don't. And so this was raising some eyebrows, and people were starting to question, are our design standards really appropriate for what we're experiencing right now? And then of course, human nature is to imagine, well, if this is happening now and we keep seeing all these headlines and the warnings from the climate scientists about carbon emissions, where are we headed from here? So this really instigated our bringing on some future weather analysis into this project. So I'm going to show a few different views of this data, but just to start out with an annual view, this is 8760 hours, comparing our traditional TMYX weather data with a future weather shift file produced by Arup. And specifically, we're using an RCP 8.5, which, if you remember back to Kylene's presentation, that's representing business as usual, sort of the worst case scenario, assuming that very little to no climate action or carbon reductions have been taken society-wide, so globally. So you can see visually inspecting this, the lines in blue are the future weather, are rising above on almost every day. We're rising above the historical temperatures. And also the minimum temperatures, the nighttime temperatures, are also elevated above the historical temperatures. So that's starting to clue us in to what's going on. Then we can look at the peak dry bulb day. So the hottest day of the year predicted by the weather file is increasing by almost 4 degrees. So it's like, we're at 3.5 degrees. We're predicting going from 95 to 98 degrees. But perhaps more importantly, and probably more consequential to the way humans experience thermal comfort, is on relative humidity. So you can see those comparison there on the left, the TMYX file with the RCP 8.5, dramatically more humid conditions are expected during those summer months of the year, which is pretty much unheard of for the Bay Area. Historically, have almost never experienced high heat and high humidity at the same time. So, looking at this, you start to think about places like the Midwest, where I'm from, St. Louis and Iowa, and some of those other hot and humid climates. So, and then another annual kind of a way to look at these two weather files annually is through the heat map that Kylene showed previously with another set of data. But basically what you're seeing here is an expansion of warm temperatures and a reduction of cold temperatures throughout the year and throughout the day. So this is our starting point going into the future weather analysis here. So on the next chart, again, we're showing a similar level of data, and we're looking to see how impactful the future climate is and against these strategies that we also consider. So charts on the left are the summary number of hours per year above 78. And the charts on the right are the histograms showing, binning the temperature data for 3 different orientations. So again, we're trying to zero in on where we should target our impacts and insulation levels and shading, as well as, this idea was, well, could we get away with only doing this partial cooling approach on one side of the building and avoid it on, say, on the north side and save some money. And so this is the framework that we use. Another view, just comparing those 3 options. We chose one zone out of our model, which is, you see down here, Unit B, number 421. And we're comparing the 3 design strategies, the heating only, the tempered DOAS, and then adding radiant cooling as well. And so we can visually inspect on the annual charts, and then we can also look at a monthly basis and see how many days per month that this overheating is occurring. And so the sort of problem months or the design months we were concerned with were August, September, October. And you can see these design strategies were having a pretty major impact on reducing the number of days that were ever reached over 78 degrees, taking it down by more than half in most cases, especially in September. And then another, deeper dive into what that data looks like. It's, not just counting the number of hours, but it's understanding when and how long the overheating is occurring. And so to me, this is where you see the most dramatic impact of seeing option 1 in the dark blue line coming up to 86 degrees on the hottest day of the year and lasting for 6 or 7 hours. Whereas with the, the proposed options we were considering, we're cutting that in half. So the number of hours were reduced by half. We're also shifting, later in the day when the overheating starts to occur, and we're finishing it earlier. So pretty impactful, and we think, would have a vastly different experience for the occupants with employing some of these strategies. So, what really matters for most projects is where the rubber meets the road is cost. And so that was really important to us as we were considering this. And again, we want to just revisit what this system really is. With the chilled ventilation, it's really a very simple strategy. We're not adding VAV boxes or additional controls. We're really just, observing the control system is observing what the outside air temperature is, and then deciding how cold should the ventilation air be. And so, there is some level of macro, it's not very granular. So every dormitory on the western or southern side are going to get the same temperature air out of the DOAS system. Very simple, very cost effective to just add a slightly larger mechanical cooling to the ventilation system. And then on the partial radiant cooling approach, this diagram is actually not quite right. It's there visually to show you that we're piping cold and hot water, but in reality, it's a switchover system. So say for the month of September, we would, instead of using or directing hot water to the radiators, we direct cold water and only make chilled water available. And so we're not adding additional valving or additional controls, additional piping. We're using the same infrastructure that would have been there for the heating only design and switching it over to partial cooling. So really the only additional cost for this is a slightly different type of a heat pump that can do both hot and chilled water. Slightly more controls up on the roof and piping up on the roof, but everything within the building is staying the same. And so really this is a very cost-effective way to address this type of situation and implement some some partial cooling to the space. And again, reminding you, we aren't, the design criteria didn't shift to be, okay, we're going to make this a fully conditioned building where we must never exceed 74 degrees during the summer. It is still a partial cooling approach, one that's seems appropriate and was deemed appropriate by the stakeholders for a dormitory building at a very minimal cost addition for this project. So we think it's a pretty successful way to do something like this, and hopefully return to this idea that a building can become maintain refuge status. So some of the takeaways here that I hope you all can embrace is that future climate analysis is not just an optional service. That's our philosophy at this point. It's really not something that we can choose to do or not choose to do. It's something that we owe as the responsible designers to bring to the surface, show to our clients and to our stakeholders. We're not just going to look up the ASHRAE design temperature and size everything to that and walk away. We want to make sure everyone has a full picture of how a building is going to operate, what the implications are going to be for the occupants. And the second bullet point is just reinforcing what we were showing at the beginning, that the climate is changing faster than the design standards we use are changing, because they're by design looking historically. They have no mechanism to look forward, and so we as designers and curious engineers need to go seek out those resources, and not just choose one resource. We need to evaluate multiple resources, like Kylene talked about. Dig into what those different concentration pathways mean and have a realistic conversation, not just assume, oh, well, California has mandated zero carbon electricity by 2045, so let's just assume that's going to happen. We need to be realistic about it. Really, at the end of the day, what we're doing here is not weighing in with our own opinions or our political affiliations. We're establishing a framework to paint a full picture of what the possible future could look like and what the outcomes to the building could look like. And so that's really, my takeaway from this, and what I hope your mindset is that we are consultants in this industry. Our job is to provide as much information and truly understand what our owners and our clients' needs are, what the occupants need, and provide them with all the information so that they can make a decision that, where to spend their money most wisely. So with that is the end of our presentation, and very thankful for you all for coming today. Hope it was useful for you. We do have a few minutes. We went a little bit long, but please ask your questions and we will do our best to answer them. It's like we've got 3 or 4 up here as well. So Mitra said, why not using AMY weather files for BDM or comfort analysis? Typical year files may reflect average conditions over a long period. So Kylene did talk about this a little bit, and others feel free to jump in. There are instances that we use an AMY file. Historically, we use that for measurement verification projects where we want to compare the way a building operated in reality against our design models. But what Kylene was mentioning is that if there's a particular year that we know was extreme, we can take that AMY file, and then you can actually apply this shifted weather, statistical science behind what is predicted, and make that AMY file into an extreme or a more extreme future weather file. So yeah, that's kind of how we would approach it.
Yeah, and I would add, I do think the TMY file is a beneficial way to look at energy modeling, because a lot of building operators and owners do want to know what's typical, right? Like what's my normal business as usual operations at the building? And I think that, that's why the TMY file was developed. But yeah, we use AMY files, I think, for specific questions or calibration of energy models. And then, yeah, kind of taking it and shifting it to the extreme.
All right. Jesse, do you want to take one here? I can read it to you, or I can address this to you. Roger asked, with the massive growth in number of data centers coming online to support new AI economy, how can we possibly make a dent in the global temps just by being more efficient with our occupied building mechanical systems?
I love this question, and I hate this question at the same time. On one hand, we try to view our impact as engineers on the global world and how, we design one dorm building or one hospital to meet that goal. And trying to say, like, how I design this dorm is going to solve all of the problems created by AI, it kind of makes it like a defeatist mentality. I like to focus on what did I do on this project and how does it compare to others? Am I moving the needle where I have the ability to move it? Because collectively, when we all have that viewpoint, then we do collectively move the needle instead of thinking, oh, well, it doesn't really matter on this one project, so why should I even try? It's not going to compete against, the big polluters of our water and air. So anyway, I think put it local on yourself and what your project can accomplish, and that is an accomplishment worth being proud of.
And just to add on to it, I think there's something like 30 to 40% of global emissions comes from buildings. So if we can even shave a few percentage points off of the emissions associated with our projects, that's going to have a pretty direct impact on the CO2 emissions into our atmosphere. So I think that's all we can do, and that's a big thing we can't do. So
I see another question asking if we are only using WeatherShift future weather files, or are we also including files from GCMs? So for maybe people that don't know, there is an opportunity to purchase these future weather files, and WeatherShift is one of those options. But there's quite a few places where you can also procure future weather files for free. I don't know, Steve, if we still have that slide we had something in our slide deck that we can show some resources that are free weather file databases where some of them are looking at, you can get free AMY files for certain sites. You can, Cura Labs is the second one. That's where we have been able to shift TMY files, or you could put in an AMY file in that case and choose from their database of GCMs and create your own free shifted weather file. But there are definitely, the national labs also have quite a few resources out there for you to kind of dig around and find weather files without having to purchase.
Well, we're over time here, so do appreciate everyone asking questions, and hopefully you all found this content useful. Please reach out if there's any other questions or anecdotes you'd like to share with us. We're always looking for ways to improve our process, and I will just want to acknowledge it's not just an interface thing that we're doing here. This approach and the way we communicate these results has come through our partnerships with our clients. I see a few WRNS folks on here. I saw them before. And that's where a lot of this thermal comfort analysis process came from. And other engineers like AirUp and other firms that are developing these processes, and a lot of smart people working on this topic. So let's all just keep doing that together, and I think we'll be in a much better place when 2050 and 2080 roll around, although I hope I'm not still working at that time. So thank you all again. Have a good one.